On May 18, 2020, heavy rainfall in Michigan raised the level of Wixom Lake, a man-made reservoir impounded by Edenville Dam, higher than it had ever gone before. As the reservoir continued to rise the following day, the dam suddenly broke, sending a wall of water downstream. As it traveled along the Tittabawassee River, the flood wave reached and quickly overpowered the Sanford Dam downstream. The catastrophic failure of the two dams impacted more than 2,500 structures and caused more than $200 million in damage. The independent forensic team charged with investigating the event released an interim report on the failures in September 2021. The conclusions of the report include a discussion of a relatively rare phenomenon in earthen dams. Let's walk through the investigation and try to understand what happened. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about the failures of Edenville and Sanford dams. Edenville and Sanford dams were two of four dams owned by Boyce Hydropower along the Tittabawassee River in Michigan. The dams were built in the 1920s to generate hydroelectricity. Edenville Dam was constructed just upstream of the confluence with the Tobacco River. It was an earth-fill embankment dam with two spillways and a powerhouse. The water impounded by the dam formed a reservoir called Wixom Lake, nearly the entire perimeter of which was surrounded by waterfront homes. State Highway 30 bisected the dam along a causeway, splitting the lake between the two rivers with a small bridge to allow water to flow between the two sections of the reservoir. Sanford Dam downstream was a similar structure as Edenville, but not nearly as long. It consisted of an earthen embankment, a gated spillway, an emergency spillway, and a powerhouse for the turbines, generators, and other hydroelectric equipment. Edenville Dam in particular had a long history of acrimony and disputes between the dam owner and regulatory agencies. Most dams that generate hydroelectricity in the U.S. are subject to oversight by the Federal Energy Regulatory Commission, or FERC. But Edenville Dam had its license to generate hydropower revoked in 2018 when the owner failed to comply with FERC's safety regulations. Their report listed 7 concerns, the most significant of which was that the dam didn't have enough spillway capacity. As a result, if a severe storm were to come, the dam wouldn't be able to release enough water to prevent the reservoir level from climbing above the top of the structure, overtopping it and likely causing it to fail. After losing the license to generate hydropower, jurisdiction over the dam fell to the state of Michigan, where disagreements about its structural condition, spillway capacity, and water levels in Wixom Lake continued. The days before the failure had already been somewhat rainy, with small storms moving through the area. But heavy rain was in the forecast for May 18th. The deluge arrived early that morning, and it didn't take long for the water levels in Wixom Lake to begin to rise. By 7 a.m., operators at the dam had started opening gates on both spillways to release some of the floodwaters downstream. Gate operations continued throughout the day as the reservoir continued rising. At 3:30 p.m., all 6 gates, 3 at each spillway, were fully opened. From then on, there was nothing more operators could do to get the floodwater out faster, and the level in Wixom Lake continued to creep upwards. That night, the lake reached the highest level in its history, only about 4 feet or 1.3 meters below the top of the earthen dam. At daybreak on May 19th, it was already clear that Edenville Dam was struggling from the enormous forces of the flood. Operators noticed severe erosion from the quickly flowing water in the reservoir near the east spillway along the embankment. Regulators and dam personnel met to review the damage, and a contractor was brought in to deploy erosion control measures. And still, the water kept rising. By 5 p.m., Wixom Lake had risen to within around a foot or 30 centimeters from the top of the dam. As crews worked to mitigate the erosion problems in other places, eyewitnesses noticed a new area of depression on the far eastern end of the dam. This part of the embankment hadn't been a significant point of focus during the flood because it wasn't experiencing visible erosion, but it was apparent something serious had happened. Photos from a few hours earlier didn't show anything unusual, but now the top of the embankment sank down nearly to the reservoir level. Eyewitnesses moved to the nearby electrical substation to get a better look at this part of the dam. Within only a few moments, the embankment failed. Lynn Coleman, a Michigander and one of the bystanders, caught the whole thing on camera. Over the next 2 hours, all of Wixom Lake drained through the breach in the dam. Water rushing through the narrow gap in the causeway washed out the highway bridge, and all of the waterfront homes and docks around the entire perimeter of the lake were left high and dry. As the floodwaters rushed through the breach into the river, the level downstream in Sanford Lake rose rapidly. By 7:45, the reservoir was above the dam's crest, quickly eroding and breaching the structure. With the combined volumes of Wixom and Sanford Lakes surging uncontrolled down the Tittabawassee River, downstream communities including Sanford, Midland, and Saginaw were quickly inundated. Google Earth shows aerial imagery before, during, and after the flood so you can really grasp the magnitude of the event. More than 10,000 people were evacuated, and flooding damaged more than 2,500 structures. Amazingly, no major injuries or fatalities were reported. In their interim report on the event, the independent forensic team considered a broad range of potential explanations for what happened at Edenville Dam. Although the spillway for the dam was undersized per state regulations, this storm didn't completely overwhelm the structure. The level in Wixom Lake never actually went higher than the top of the embankment. So overtopping, one of the most common causes of dam failure, including the cascading loss of the downstream Sanford Dam, was eliminated as a possible cause of failure for Edenville Dam. The team also looked at internal erosion, a phenomenon I've covered on this channel before that has resulted in many significant dam failures. Internal erosion involves water seeping through the soil and washing it away from the inside. However, this type of erosion usually happens over a longer time period than what was witnessed at Edenville Dam. No water seepage exiting the downstream face of the embankment or eroding soil was evident in the time leading up to the breach, ruling this mechanism out as the main cause of failure. The forensic team determined that the actual cause of failure was static liquefaction, a relatively unusual mechanism for an earthen dam. Soils are kind of weird, but don't tell that to the geotechnical engineers. Because they're composed of many tiny particles, they can behave like solids in some cases and liquids in others. Of course, most of our constructed environment depends on the fact that soils mainly behave like solids, providing support to the things we build on top of them. Liquefaction happens when soil experiences an applied stress, like an earthquake, that causes it to behave like a liquid, and it mostly happens in cohesionless soils, those where the grains don't stick together, such as sand. When a body of cohesionless soil is saturated, water fills the pore spaces between each particle. When a load is applied, the water pressure within the soil increases, and if it can't flow out fast enough, it forces the particles of soil away from each other. A soil's strength is derived entirely from the friction between the interlocking particles. So, when those grains no longer interlock, the ground loses its strength. Some of the most severe damage from earthquakes comes from the near instant transformation of underlying soils from solid to liquid. Buildings sink into their foundations, sewer lines float to the surface, and roads crumble without underlying support. Liquefaction typically requires cyclical loading, like during an earthquake, or extreme sudden displacements to trigger the flow. Gradual increases in loading will only cause the water within the soil to flow out, equalizing the pore water pressure. But some soils can reach a point of instability and liquefy under sustained or gradually increasing loading conditions in certain circumstances. This phenomenon is known as static liquefaction. A good analogy is the difference between glass and steel. Both materials have a linear stress-strain curve at first. In simple terms, the harder you push, the harder they push back. But both reach a point of peak strength, beyond which a soil will fail or deform. Well-compacted sand is like steel. It fails with ductile behavior. If you stress it beyond its strength, it deforms, but the strength is still there. In other words, if you want to keep deforming it, you have to keep applying a force at its peak strength. On the other hand, loose sand is like glass. If you push it beyond its peak strength, it fails with brittle behavior, suddenly losing most of its strength. The independent forensic team took samples of the soils within the Edenville Dam embankment and subjected them to testing to see if they were liquefiable. The tests showed brittle collapse behavior necessary for static liquefaction. They also reviewed construction records and photographs where no compaction equipment was seen. The team concluded that as the level of Wixom Lake rose that fateful May evening, it increased the hydraulic load on the embankment, putting more stress on the earthen structure than it had ever been asked to withstand. In addition, the higher levels may have introduced water from the reservoir to permeable layers of the upper embankment, as evidenced by the depression that formed before the failure, increasing seepage and thus increasing the pore water pressure of saturated, uncompacted sandy soils within the structure. Eventually, the peak strength of the embankment soil was surpassed and a brittle collapse resulted, liquefying enough soil to breach a downstream section of the dam. A few seconds later, lacking support from the rest of the structure, the dam's upstream face collapsed and all of Wixom Lake began rushing through. Edenville Dam was built in the 1920s, before most of our current understanding of geotechnical engineering and modern dam safety standards existed. Most dams are earth and embankment dams, but modern ones are built much differently than this one was. Embankments are constructed slowly from the bottom up in individual layers called lifts. This lets you compact and densify every layer before moving upward, rather than just piling up heaps of loose material. We use gentle slopes on embankments to increase long-term stability, since soils are naturally unstable on steep slopes. We have strict control over the type of soil used to construct the embankment, constantly testing to ensure the properties match or exceed the assumptions used during design. We often build an embankment of multiple zones. The core is made of clay soils that are highly impermeable to seepage, while the outer shells have less stringent specifications. We include rock riprap or other armoring on the upstream face so that waves and swift water in the reservoir can't erode the vulnerable embankment. And we include drains that both relieve pressure so it can't build up within the soil and filter the seepage to prevent it from washing away soil particles from inside or below the structure. Edenville Dam actually did have a primitive internal drainage system made from clay tiles, but many of the drains in the area of the failure appeared to be missing in a recent inspection. Although it seems like an outlier, the story of Edenville and Sanford dams is not an unusual one. There are a lot of small old dams across the United States built to generate hydropower in a time before everyone was interconnected with power grids. Over time, the revenue that comes from hydropower generation gradually declines as the maintenance costs for the facility and the danger the dam poses to the public both increase. However, the reservoir created by the dam is now a fixture of the landscape, elevating property values, creating communities and tourism, and serving as habitat for wildlife. You end up with a mismatch of value where most of the dam's benefits are borne by those who don't incur any responsibility for its upkeep, or liability for the threat it poses to downstream communities. Even owners with the best intentions find themselves utterly incapable of good stewardship. Combine all that with the fact that regulatory authorities are often underfunded and lack the resources to keep a good eye on every dam under their purview, and you get a recipe for disaster. After all, there's only so much you can do to compel an owner to embark on a multi-million-dollar rehabilitation project for an aging dam when they don't have the money to do it and won't derive any of the benefits as a result. Since the failure, the dam owner, Boyce Hydro, filed for bankruptcy protection, and the counties took control of the dams with a nonprofit coalition of community members and experts to manage repair and restoration efforts. Of course, there's a lot more to this story than just the technical cause of the failure, and the final independent forensic team report will have a deeper dive into all the human factors that contributed to the failure. They expect that report to be released later in 2021. Dams are inherently risky structures, and it's unfortunate that we have to keep learning that lesson the hard way. Thank you for watching, and let me know what you think.